When you're operating on the fire ground, it's important to understand that high pressure gases flow to low pressure. This is a basic fire dynamics principle that explains why ventilation works. As a fire develops in a compartment, the heated products of combustion expand, creating an increase in pressure. When you make ventilation changes to the structure by opening a door or taking a window, you're creating a new low pressure and a flow path. A flow path is the areas within a structure where heat, smoke, and air flows from an area of higher pressure to lower pressure. It's composed of at least one intake vent, one exhaust vent, and the connecting volume between the vents. This flow path can be used for your tactical advantage, such as indicating the location of the fire for the advancing hose crew, or to your detriment as hot gases flow from a bedroom fire to a door, passing over your search crew, forcing a retreat. Here's an experiment that's an excellent example of fire flowing from high pressure to low pressure during different stages of the fire. We ignite the fire in the living room on the first floor of this two-story townhouse. As that fire increases in size, the temperature increases, which increases the pressure, which has the products of combustion flow out of that second floor window that's halfway open. You'll see light smoke start to come out of that second floor window as that first floor pressure increases. That window acts as the low pressure and will continue to do so until the fire on the first floor runs out of oxygen. Once the fire on the first floor runs out of oxygen, it's going to change the pressure. It's going to be looking for oxygen, so it's going to try and pull oxygen from around the front door. You'll see the smoke puffing at the front door. When it can't get any oxygen through that front door, the temperatures are going to decrease. As the temperatures on the first floor decrease, the pressure decreases. As that pressure decreases, it's actually going to go into a negative pressure. As you see, no more smoke is coming out of that second floor window until the first floor door gets opened. Once that door gets opened, creates a new flow path. Air goes in the lower half of the door, hot gases come out the top half of the door, and as that fire begins to increase in size, you also get those gases flowing up that second floor to the low pressure out of that bedroom window, leading this fire to transition to flashover. Firefighters know that a fire needs fuel, heat, and oxygen to sustain. When you were introduced to the fire triangle, you were probably introduced to the stages of fire development: ignition, growth, fully developed, and decay. This rings true when you make a campfire or when you have a piece of furniture on fire in a parking lot, because the fire will have access to a supply of oxygen all around it. There's a big difference between fighting fires in parking lots and fighting fires in enclosed structures. Because modern home furnishings burn faster, consuming oxygen faster, and release energy faster than in the past, today's fires grow until they become ventilation limited. Fire development changes when a fire becomes ventilation limited. At this point, when the fire department arrives, there may be nothing showing, but if there's still heat and fuel, once oxygen is reintroduced, the fire will grow rapidly to a ventilation-induced flashover. If the fire department arrives and there's fire burning outside of the structure through windows or doors, the fire is still ventilation limited. In other words, if additional vents are made, the fire will continue to increase in size. It's very unlikely that you can ventilate your way out of a ventilation-limited fire, because adding more air usually just allows more fuel to burn, releasing more heat. Fuel and heat definitely contribute to fire growth, but it's the amount of oxygen that makes the difference in how fast fire is allowed to release heat. Control the oxygen, and you have control of the fire. In this video, we measured the heat release rate of two rooms. One furnished like a typical living room, and one filled with chairs and sofas. Both rooms go to flashover, and even though one has significantly more furnishings, they both have the same heat release rate, around 7 megawatts, because the size of the fire is limited by the amount of ventilation or the size of the opening on the front of the room. The room with more furnishings will burn longer, but it won't release more energy unless more air can enter the room by creating another opening. This occurs later in the comparison as the ceiling begins to fail in the over-furnished room, allowing more air in. More products of combustion out, and the heat release rate goes up. This is the same as if you arrive on the scene with fire out of one window. Venting a second window lets more air in to increase the size of the fire, so coordinate water on the fire to stop that fire growth.
A good incident action plan involves an understanding of where the fire is located and where it is spreading. Fire gases and heat will move from an area of higher pressure, typically where the fire is, to an area of lower pressure. This path of smoke and heat spread is known as the exhaust portion of the flow path. In a structure fire, a flow path exists between the fire and an area of high pressure and any adjacent room, hall, stairway, open door, or window that connects to an area of lower pressure. During fire suppression, firefighters have the opportunity to take advantage of how water streams can alter this flow of smoke and heat. In some instances, it is advantageous to alter the flow. For example, during an interior attack when there is a vent opposite the advancing hose crew. Entraining as much air as possible with the hose stream creates pressure that can push the products of combustion ahead of the advancing crew. In other instances, for example, during an exterior water application, it can be more effective to cool and knock back the fire using streams and nozzle handling techniques that limit air entrainment and pressure buildup. This limits the impact on the flow path and allows the exterior vent to continue to function as an exhaust vent. Flow path and fire suppression must be thought of together. Knowing how and when to alter the flow path makes for a more effective and safer fire attack.
When there's fire venting from the A side, near the entry door, with no other openings on the structure, it's easy to determine the location of the fire. In this scenario, a transitional attack may be the most effective way to knock back, confine, and suppress the fire. In this scenario, the fire is venting from the side A window near the door. No other vents are open, and the neutral plane is above the sill of the window. The lack of additional vents and neutral plane position indicate the seat of the fire is located in that compartment. When a transitional attack is chosen, the most effective method of initial water application to coat the most surfaces, thus providing the most cooling, is as steep of an angle as possible off the ceiling. Keep the nozzle as steady as possible. The nozzle firefighter should be constantly evaluating the effectiveness of water application, looking for indications that it's having an effect. The flames in the gas layer should begin to extinguish within seconds. If no effect is noted, the nozzle should be directed in a different location, or possibly off the top of the window to coat surfaces. Once the gases have been cooled enough to no longer have fire venting out the window, the nozzle can be shut down to evaluate those conditions. There is no specific time limit or suggested flow time, as the time required for cooling should be based on conditions. If the water application is no longer showing signs of effective cooling, the application angle should be adjusted. Once the gases have been cooled and the nozzle shut down, the nozzle firefighter should apply water to any visible flame in the compartment. If visibility is limited, a half bale or narrow fog should be applied through the window in a wide O pattern to coat the most surfaces. Care should be taken to limit air entrainment by ensuring the nozzle is placed inside the window. If the suppression crew cannot apply water directly due to an obstruction near the opening or the elevation of the window, such as a second floor fire, or if the tactic is ineffective, they should rapidly transition to the interior once the gases are cooled. While relocating the line to the front door, the crew should pay attention to the conditions at the front door, evaluating for the conditions which indicate transitional attack was not effective. Consideration should be given to the line used for final interior suppression. The crew should utilize the most rapid method of transitioning. In some instances, this will be by relocating the initial attack line to the interior, and in others, it may be deploying an additional line for interior suppression. If more than one crew is available, consideration should be given to conducting simultaneous exterior application and interior advancement.
Many firefighters have been taught that all hose streams can push fire. Therefore, you must always fight fire from the unburned side. Some firefighters have even experienced fire being pushed on them. But what does pushing fire mean? Pushing fire. When fuel gases, hot enough to burn, are displaced or pushed by pressure from an oxygen-limited fire compartment to a space with oxygen that mixes with the hot fuel gases and results in combustion. What conditions do you need to push fire? Well, typically, you need a ventilation-controlled fire in a flow path that has intake and exhaust vents. Then you need a pressure source to create the push. In addition, you need an area on the low pressure side that has oxygen available for combustion. If you do not have these conditions, you cannot push fire. The pressure source could be from the wind, a fan, a fog stream, or a solid stream on a hand line that's being whipped around. If you review our research studies, we've conducted studies with each of these sources of pressure, and you'll see that even a small increase in pressure can drive hot fire gases through a space at speeds ranging from 6 miles an hour to greater than 20 miles per hour. There are situations where firefighters may want to use this push to their advantage when fighting a fire. Working with ISFSI and the Spartanburg Fire Department, we set up some tests to demonstrate pushing fire and also to show how it is important to choose your hose stream wisely and use it effectively for times when you want to avoid the push, the buildup of pressure. This video shows a post-flashover room fire in the rear of the structure. The rear room window is serving as both an intake and an exhaust vent for the fire room. The middle room is connected to the fire room by an open doorway. The middle room is also serving as an exhaust-only vent because the windowsill height is above the neutral plane. Note that the exhaust gases have enough heat and fuel to burn, but they don't mix with enough oxygen to burn until they are above the eave line. The fog stream is going to minimize the water entering the fire room, maximize the air entering the fire room, and provide the air pressure needed to push. Let's look at another experiment. Here we have two rooms on the second floor of a house. Both rooms are similar in size and had similar fuel loads, consisting of a wood bed frame, mattress, box spring, wood dresser, and pallets. The interior finish of the rooms in the connecting hallway at the top of the stairs consisted of wood paneling and oriented strand board on the walls, gypsum board and OSB on the ceiling, and wood flooring. The open doorways from each bedroom are opposite each other at the top of the stair. The doorway to the exterior at the bottom of the stairway is open. The cameras are located in this doorway looking up the stair. This door will serve as an air intake for the fire upstairs. The upstairs windows are the only point of exhaust initially in the fire, as the smoke building in the hallway does not have enough pressure to push all the way down the stairs against the intake flow of the air. The beds in both rooms were ignited at the same time and the fires began to develop. When both rooms had reached the fully developed fire stage, based on the available ventilation, gas temperatures near the ceiling were in excess of 1,000 degrees Fahrenheit, and the command to initiate water flow was issued. On the right-hand window, 150 gallon per minute straight stream was flowed. The straight stream was deflected off the ceiling to cool the gases in the room. The straight stream was then applied with minimal movement. This stream choice and nozzle handling technique maximized the amount of water entering the fire compartment, minimized the entrainment of air due to the hose stream, and kept the vent area of the window as open as possible to maintain the window as a low pressure exhaust vent. This allows combustion products and steam out of the window even though the line is flowing. The result? Little to no impact on the fire in the hallway at the top of the stairs, and a temperature decrease from the peak temperature at the ceiling in the right room from approximately 1,000 degrees Fahrenheit down to 300 degrees Fahrenheit. Next, a 150 gallon per minute fog stream, wide enough to cover the window, was flowed over the left-hand window on the second floor. The idea was to cover the vent, which minimized the amount of water that entered the fire compartment and increased the amount of air that was entrained into the fire compartment, and increase the pressure at the window vent, thereby blocking the vent. Initially, this caused a surge of heated gases and smoke to be pushed down the stairs, as well as an increase in temperature in the fire compartment. As the fog nozzle was moved forward, more water began to enter the compartment and the temperature began to decrease. The fog stream created a higher pressure area at the window, effectively turning the exhaust vent into an intake. This added extra air for combustion, and it was an ineffective amount of water. In other words, not enough to cool the fire compartment, and therefore it converted to steam. This combination increased the pressure in the fire room and caused a quick burst of heat and flame to push down the stairs. When the fog stream was narrowed and moved forward, more water entered the fire compartment, the pressure at the window reduced. Cooling the fire reduced the pressure created by the fire itself and caused some of the fire gases to contract. As a result, the high pressure push stopped. So we've shown that you can push fire with a hose stream if the air from the stream creates a higher pressure area and the lower pressure area has oxygen available for combustion. However, we can also see that this can be prevented by the use of a solid or straight stream with limited movement if you're attacking from the exhaust side. If you're working in the interior and attacking toward the exhaust, you may want to use air pressure to your advantage to force heat away from your position and out another exhaust vent. Basically, it's all a battle of the pressures, pushing fire. When fuel gases hot enough to burn are displaced from an oxygen-limited compartment to a space with oxygen that mixes with the hot fuel gases and results in combustion. Please see our studies on ventilation, positive pressure ventilation, and fire attack so you can get a better understanding of the pressures created by a fire inside a structure, the impact of wind, the impact of fans, and the impact of hose streams, so you can make good choices on the fire ground.
At this point, we've all heard how synthetic furnishings and the evolving methods and materials used in building construction are continuing to change the fire environment, leading to new challenges for the fire service. Fires today grow and spread faster than ever before. Where previously fires may have grown steadily from ignition to flashover and a fully developed state, today's fires are controlled by the amount of ventilation and oxygen available. As the fire grows rapidly, the available oxygen within the space is consumed and the fire transitions to an underventilated state, where the temperatures and pressures within the home begin to decline. This often occurs before the fire has ever even reached flashover. The available oxygen within homes today is often limited due to the construction practices which focus on energy efficiency, leading to tighter buildings and minimal leakage. Because of the lack of oxygen within the home, the fire is now starved for air, and any change in ventilation provides a new supply of oxygen, which can lead to rapid fire growth and minimal reaction time for firefighters. One of the consistent themes seen throughout the research to date is the concept that ventilation must be coordinated with suppression. Coordination on the fire ground begins with the very first fire service intervention, which is typically when the arriving crews force the front door for entry. Knowing that the fire is most likely in a ventilation-controlled state, firefighters must be aware that opening the front door for entry is providing the fire with a new source of oxygen. Conditions may begin to deteriorate as the fire begins to regrow and move towards the front door. The speed of regrowth and the reaction time for firefighters occupying the space is all dependent on the proximity of the fire to the now open vent. The opening of the front door should be coordinated with a charged hose line and firefighters dressed and ready for entry. Depending on the extent of fire development prior to going vent limited, the fire may regrow quick enough to prevent firefighters from entering the building. However, many times firefighters are able to enter the structure to begin search and rescue before the fire makes it to the front door. This can place firefighters in a dangerous spot as they advance down the flow path to the seat of the fire. Firefighters should always be aware that once the front door has been opened, a new flow path has now been created and the fire will continue to grow and move towards this open, low-pressure vent until it's controlled via suppression. Forcing the front door needs to be considered in the same way as any other form of horizontal ventilation. In many cases, the front door can allow for quicker regrowth because the open doorway goes to the floor, which allows the denser, cooler air to work its way in low along the floor when compared to a window which is higher in the space and less efficient at entraining air. Prior to opening the door for entry, crews must ensure that face pieces are on, firefighters are breathing air, and lines are charged so that the transition to the interior can occur quickly. Don't forget to make a quick observation of conditions at the front door when you open it. Where is the neutral plane? Do you notice any fresh air being drawn in or any gravity current to point you in the direction of the fire? What is the smoke doing? How about the color, density, and velocity? As you enter the building, you must be aware that you are now entering into a new flow path, which means that the fire is going to be growing and coming towards you, seeking the path of least resistance until water's flowing and you've gained control of the situation. If the front door is open for firefighter entry, it's also open for air. Tactical discipline with forcible entry and coordination with suppression are key.
We all know that gases in a compartment of higher pressure will naturally flow to compartments of lower pressure until the pressure zones equalize. When wind is impacting a building, it is creating a higher pressure on the upwind side of the building, and it is generating a lower pressure on the downwind side. This phenomena can be seen in the simulation shown from a line of duty injury that occurred in Prince George's County, Maryland. Wind speeds as low as 10 miles per hour can increase the heat release rate of the fire and generate gas flows that fill doorways, rooms, and corridors with a unidirectional flow of hot gases or flames that can extend from the ceiling all the way down to the floor. In a wind-driven fire, the area downwind of the fire room is the exhaust portion of the flow path. Firefighters have referred to this as the blowtorch effect. Working with FDNY, the Chicago Fire Department, and the Toledo Fire Department, we measured conditions on the downwind side of a wind-impacted fire in excess of 1,000 degrees Fahrenheit with heat flux values in excess of 70 kilowatts per meter squared. These conditions would likely result in a fatal injury to both civilians and fully protected firefighters alike. The message is simple. Consider the wind as part of your size up and keep the wind at your back. This will help you make an effective attack and enable you to make entry and complete your search faster.